Hi, we're on part 2 of section 9.2, and we're talking about microbial control, and we're going to start on radiation. And I just want to go use this diagram here with the electromagnetic spectrum. So these are the different wavelengths that you have in the electromagnetic spectrum, and we take advantage of the visible light range all the time. And so you can see that in there. But if we go to the broader wavelengths, you can see the lower energy wavelengths. We have infrared, microwaves, and radio waves. I actually have microwaves listed under microbial control in the heat section. And the bottom line about microwaves is that what went on for a little while that people were recommending that you put your kitchen sponge in the microwave to decontaminate it. And it works pretty well. It kills microbes quite effectively. But some people left their sponges in there a little bit long, they got dry and they caught on fire. So then there were other messages that said, hey, wait a minute, maybe you better not put your sponge in the microwave. It turns out that the microwaves themselves are not antimicrobial to any great extent, but they create a good amount of heat, and that heat will actually kill the microbes in your sponge or whatever you put in there. So I have microwaves listed under heat, and it's not the microwaves themselves that are antimicrobial. But once we get to these wavelengths below visible light, these are antimicrobial. And there's that kind of pinkish color showing you that we have some sterilization going on here. So we have ultraviolet light, UV light, which we also call non-ionizing radiation. And then we have ionizing radiation, which is the X-rays and the gamma rays. So I'm going to talk right here about ionizing radiation, the X-rays and the gamma rays. And you can see here that these are increasing energy. These are the higher energy waves. And this radiation is very effective at penetrating. It's telling you somewhere in here that the X-ray, the gamma rays are the most penetrating. I can't remember where it is in here, but the gamma rays are the most penetrating, and the X-rays are kind of intermediate, a little bit less penetrating. But the gamma rays and X-rays is a very effective way to sterilize. In fact, a lot of the things that we buy for the laboratory, we buy like whole sleeves of petri dishes. They're in kind of a pile inside of a plastic bag, and they're already sterile. And these petri dishes have been put in bags and then put in boxes. So I have a case of petri dishes sealed, and then they're put into a device that generates gamma radiation. And that gamma radiation penetrates the box and penetrates the plastic bag and penetrates the petri dish and sterilizes the inside and outside of the petri dish. Pipettes and lots of other tools that we use in the laboratory have been sterilized using gamma radiation. Now, just like if you shine light on your skin and then you turn the light off, you don't have light residue on your skin. The same thing is with this radiation, that if you expose petri dishes or whatever to that radiation, there's no residue left on there. It's just the waves themselves that actually cause the antimicrobial effects. So we can sterilize, we can inactivate endospores with gamma radiation. Another place that you're going to see this ionizing radiation, this highly penetrating radiation, is related to food. And it says from flour to pork to ground beef to fruits and vegetables, radiation is occasionally used in microbial control in food. In fact, I noticed in the grocery store in Wegmans, you can buy the regular hamburger in the meat section, or you can go to the freezer section and buy the irradiated hamburger. And that hamburger, I don't know if it's actually sterilized, but I'd imagine it is. And so it's going to actually last a lot longer in the refrigerator if you buy the irradiated meat. There's situations where they use radiation to decontaminate certain fruits and vegetables, so and to increase the shelf lives. And people don't love the idea of their food being irradiated. There is some evidence that there's a little reduction in vitamin B1 but it's not really that big of a reduction. It shouldn't be of any major consequences. And some foods don't survive radiation very well, but it is something that can be done to reduce microbes in food. The other one that's commonly used is non-ionizing radiation in the form of UV light, ultraviolet light. And just like our table here shows, ultraviolet light, it has a lower energy than gamma rays or X-rays. And therefore, ultraviolet light is very effective at microbial control, but it doesn't penetrate. So I couldn't get the inside of a petri dish sterilized using UV light, or the inside of a hamburger. And that's that kind of reflects on how we use ultraviolet light. Ultraviolet light can sterilize as long as it's just exposed, just a surface is exposed. But most things have, nooks and crannies or corners and things like that. So they even though ultraviolet light is capable of sterilizing, they'd say, oh, it's close to sterilizing, not quite, and kills most microorganisms. Things that we would use for UV light for reducing microbes. I know in the laboratory, a lot of times when you're transferring microorganisms, in some laboratories, when you're all done, they'll shine a UV light on the surface to kill any microbes that were left there. We can use UV lights in hospital rooms, operating rooms. If you look down here, here's one of these robots that they're now using in hospital rooms. The UV light can move through the air, so it can kill microbes in the air or microbes on surfaces. So these are showing up in hospitals more and more frequently, and they're very effective at microbial control. There's UV light. I've seen examples of it used to kind of reduce the number of microbes in things like apple cider. And this is a machine, it's kind of hard to see what it's doing, but it makes these real thin sprays of the liquid that it's decontaminating, exposing it to UV light. And because the stream of liquid is so thin, it's essentially all surface, and the UV light can reduce the pathogens in that. So there are pieces of equipment that you put apple cider through like that, and it can preserve the quality of the taste of the apple cider while reducing the number of microorganisms in it. Just a reminder that radiation is potentially very dangerous. It damages DNA, and it goes into some details about how it does it, which doesn't matter to me if you know that. But radiation, whether it's ionizing or non-ionizing, causes damage to DNA and can potentially cause cancer. And that's why we try to stay out of UV light for our skin. When they use these robots in hospital rooms, these rooms are blocked off so nobody can enter. This is very dangerous. It can damage your eyes, it can damage your skin. And so you can't be in a room when this is turned on. The next method of physical control of microorganisms I'm going to talk about is filtration. And so filtration, you'll use some kind of filter. And so that's what they're showing you here is a filter that has very tiny holes through it. So the holes are big enough for the liquid to pass through, but not big enough for microorganisms to pass through. And so we can take a liquid and pass it through this filter and have sterile liquid coming out. And if we're going to use our definition of sterile to be free of viruses, then some viruses can probably pass through here. But for most of the time when we're using filters, we're concerned with removing bacteria. So here they're showing you an example of what we call a membrane filter. This is kind of just looks like a real thin piece of paper. And there's a electron microscope picture of it. There's the little holes in it. And so here you put your liquid here, there's your filter, and then you put it on this flask, and there's a suction that sucks your liquid through this filter, and you have your sterilized fluid down here. So membrane filters are really handy. If you have a solution that can't be sterilized by heating, then you might want to filter it through a membrane filter. And I've worked in research labs where we do a lot of that. Membrane filters are really common. Talks a little bit about the size of the pores and all that here. The other kind of filters that, oh, and here's some more examples of things that you could sterilize through a membrane filter. Blood serum and other blood products, vaccines, different fluids, enzymes, and whatnot. But these would be things that would be sensitive to heating. The other kind of filter that we use frequently are HEPA filters. And HEPA filter is a high efficiency particulate air filter. And those HEPA filters are designed to filter air. And you might have a HEPA filter on your vacuum cleaner or on your air ventilation system in your house. In clinical settings, we could use a HEPA filter to sterilize the air going into an operating room, or sterilize the air going out of a room that contains patients that have a contagious disease. So if you have measles or tuberculosis, they might put you in a special room that has filtered air. So HEPA filters can be used in all sorts of situations. The last thing we're going to talk about with physical control of microorganisms is osmotic pressure. And we kind of talked about this already when we talked about microbial growth and osmosis. Remember that hypertonic environments, high salt or high sugar, hypertonic environments can stop microbial growth. Remember, we had the pictures of the cells shriveling up. Even though they have a cell wall, hypertonic environments can cause bacteria to shrivel up and die. And so here it says a large amount of salt or sugar in foods can create this hypertonic environment and plasmolysis, shriveling up of cells, and the bacteria won't multiply. It won't necessarily reliably sterilize, but you can do very effective microbial control with that. And here's a picture of some sardines in a can that by adding salt to them, it can contribute to their ability to be preserved for long periods of time. Think of any foods that, they have a lot of nutrients, jelly or peanut butter or ketchup or I don't know, a lot of things that you could actually leave at room temperature. Crackers, you could leave at room temperature. Even though there's lots of nutrients there, microorganisms aren't going to grow in them because they're hypertonic. They've got a lot of sugar or they've got a lot of salt. I do like this little comment that says even in ancient time, people used pickling, smoking, and drying food to control the growth of microorganisms. They don't know why it worked. They didn't know that. They just knew their food didn't spoil. And eventually they figured out, oh, microorganisms cause spoilage. And adding these things, pickling and smoking and drying, prevented them from microbial growth. So at that point, I'm going to stop section 9.2.